Can you guys hear me and see the screen? Can you guys hear me and see the screen? Branch, can you hear me? Joshua, can you hear me? Can you hear me now? Can everyone hear me? Hello? 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 Branch, can you hear me? Can you hear me? Hello?
Good morning, Professor.
Hello? Can you hear me?
Yes.
Okay, good morning. There's some feedback in the audio. I don't know why. Hopefully it's not too bad. I don't know if it's better now. Hope you guys can hear me and see the screen. If not, unmute yourself and let me know. All right, good morning. So last week, we were talking about capacitance voltage behavior of MOS structures. From this week, we'll talk about current voltage behavior of MOSFETs. But just as a preview, we'll first briefly talk about current voltage capacitor behavior of the MOS capacitor itself, formed by the gate electrode, the gate dielectric, and the semiconductor channel. The issue can be seen if you look at the formula for a parallel plate capacitor shown over here. C is equal to, for a capacitor of area A, the capacitance would be the area times the dielectric constant, which in turn can be written as a free space dielectric constant epsilon naught times the relative dielectric constant of the semiconductor epsilon r. Epsilon naught, epsilon r combined give you your epsilon of the dielectric divided by the thickness of the dielectric. Of course, so far, we've been largely talking about capacitances per unit area. So you can set A equal to 1. And then if you want the total capacitance, you simply scale it up by the area of the capacitance, okay? And we'll see today, when you look at MOSFETs, that the current of a MOSFET is proportional to the gate capacitance, okay, Cox. And that kind of makes sense because the larger the value of the Cox, that means that the gate is coupled more strongly to the channel, and therefore it can induce more carriers in the inversion layer for a modest gate voltage. And that's what you want, because you want to be able to operate the device at as low of a voltage as possible. Now, the challenge that people face in this industry in the 1990s is the following. You want the gate capacitance, Cox, to be as large as possible. And for many decades, that was achieved by making the gate oxide, Tox, thinner and thinner and thinner, okay? But the oxide, which is of course an insulator, provides a barrier to current flow from the gate. If I plot the cross section over here for a second, So that's my gate, that's my oxide, and then I have my source drain. So we are looking at, of course, this capacitor structure. Okay. Now this oxide provides a large energy band gap. The gate doesn't have a band gap. It has the work function in the metal, and the semiconductor channel has a lower band gap. So hopefully carriers can flow across this barrier because this insulator is a very large band gap material. Okay. But of course, we studied in chapter 2 that as you make this barrier thinner and thinner and thinner, carriers don't necessarily have to go over the barrier, but they can simply burrow or tunnel through the barrier. Okay. And the tunneling current we've seen depends not only on the height of the barrier, but also the thickness of the barrier. So that's the problem that people face, that as gate oxides are made thinner and thinner and thinner, we increase the gate capacitance, which is necessary to couple the gate to the channel so that you can have more inversion carriers in the channel. At some point, the leakage current, the tunneling leakage current to the gate dielectric became a problem. And that's kind of what's shown over here. In terms of current density, the leakage current density through the gate itself in amps per centimeter square as a function of the applied gate voltage for different oxide thicknesses. So as you see, for a certain oxide thickness, as you make the gate oxide thinner, there's more and more leakage current in the system. Okay. The leakage current also increases with the gate voltage, because higher the gate voltage, higher will be the electric field across the oxide, and that also causes additional leakage current due to tunneling. Okay. So to get out of this problem, around mid-90s, people started looking at what are called alternative gate dielectrics, which have a higher dielectric constant than the usual dielectric, which is SiO2. Okay. SiO2 has a relative dielectric constant of 3.9 or approximately 4. Okay. So people said that, okay, instead of keeping on reducing the silicon dioxide thickness and suffering from this tunneling problem, why not use alternative dielectrics? Okay, these are generally known as high K gate dielectrics, where instead of a relative dielectric constant of 4, you have much higher dielectric constants. Okay, and the current champion is something called hafnium dioxide, which has a relative dielectric constant of approximately 25. Okay, let's say 24, so 6 times as much as oxide. Okay, so in that case, for the same physical thickness of the dielectric, when you go from silicon dioxide to hafnium oxide, your oxide capacitance then would go up by a factor of 6. Okay, which is good. So then what you can do is you can then back off on scaling down the hafnium oxide thickness. You can afford to make the oxide thicker. So now that's my gate, that's my hafnium oxide, and that's my silicon channel. So you can make this oxide thicker and still have a high oxide capacitance, because now I have a higher relative dielectric constant. Dielectric constant is also sometimes known in physics as the parameter K. That's why these are known as high K gate dielectrics. All right. So that's the basic idea. You move away from oxide, silicon dioxide, to other kinds of oxides, and hafnium oxide is one of the most popular choices these days. Now, you guys, if you get into the field, you may discover some other oxide which is even better. Now, it turns out things are not quite as rosy as it may sound, because in silicon dioxide, if you look at the band diagram, notice I'm drawing the band diagrams flipped, okay, by 90 degrees. Normally, we've been drawing the band diagrams like so. So I'm drawing it flipped to kind of correspond to these structures over here. So in this oxide, we know that the band gap is around 9 electron volts, okay? And the band offset between the conduction band of the oxide and the conduction band of silicon is about 3 electron volts, okay? On the other hand, in the case of hafnium oxide, the band gap shown in this direction is much smaller. It's about 5 to 6 electron volts. And therefore, the barrier between the conduction band of the silicon and the conduction band of the hafnium oxide will be smaller. So although it's true that you're getting a wider tunneling barrier, the height of the barrier is less. So it's not, you have to be very careful that you make sure that you have a good combination of not just the thickness of the tunneling barrier, but also a high enough barrier. And it turns out hafnium oxide works pretty well, both for the electrons in the conduction band and the holes in the valence band, okay? The other challenge that, however, people have faced is when you switch from SiO2 this to hafnium oxide, this interface between the silicon and the dielectric generally tends to be worse than between silicon dioxide and silicon. The silicon dioxide silicon interface is one of the best electronic interfaces that you have in the world. Okay, other dielectrics are not quite as nice, and as we'll see today, that then impacts the mobility of carriers traveling in the inversion layer from the source to the drain. Okay, so the key equation is over here. As you make the alternative high K dielectric constant higher than that of the silicon dioxide, which is sort of the canonical dielectric, you can modify the dielectric thickness compared to the oxide dielectric thickness without sacrificing gate capacitance. So the physics of tunneling is shown by these band diagrams over here. Now I'm drawing the band diagrams the usual way, okay, where energy points upwards, and this is position. So if I was to look at the MOS structure, my gate would be over here. That's my metal gate. That's my oxide. And then I have my silicon over here, okay? So as you increase the gate voltage, I mentioned that the electric field across this region increases, and that's shown by a steeper and steeper slope, because the slope of the band edge is a measure of the electric field. And you can see clearly then an electron in the metal gate can tunnel through more and more easily as the gate oxide field becomes higher and higher, okay? Or if the oxide becomes thinner, the barrier height becomes smaller and the tunneling current goes up, all right? And it turns out, although we won't necessarily get into the details, there's two flavors of this tunneling. One, where the oxide thickness is thick enough such that the tunneling barrier that the electrons face, which is shown by this blue line, is more like a triangular barrier. And that flavor of tunneling is known as Fowler-Nordheim tunneling, after the two physicists who studied that. But if you make the oxide much, much thinner, they don't have to go into the conduction band of the oxide and then go down. They can go straight directly through the oxide and appear in the silicon. And that flavor is known as direct tunneling, okay? And the overall physics is more or less the same, but the exact current voltage dependencies are slightly different. If you go through the physics, the Fowler-Nordheim tunneling current scales as the electric field square in the oxide times e to the power minus a constant V divided by the electric field, okay? And if that is your dependency, you can replot it in a funny way, okay? You can divide both sides by electric field square and take the log of both sides. If you take the log of an exponential, you simply get this. So log of current divided by electric field square plotted as a function as 1 over electric field over here should then give you a straight line whose slope would depend on this parameter B, which it turns out depends on the height of the barrier, say here in the conduction band for the electrons. So it'll depend on delta C and the effective mass with which the carriers tunnel through the barrier, okay? Now this effective mass is different from the density of states effective mass, the effective mass that you have for conductivity in the semiconductor, okay? This is known as your tunneling effective mass. Ultimately, you get it from the band curvature effective mass, but it's a slightly more complicated scenario. So it's not quite the same effective mass as in density of states or conductivity effective mass. It's your tunneling effective mass. Now, when you have such tunneling, unfortunately, because the mobility of carriers in the oxide is very, very small, just to give you a calibration, the mobility of electrons in silicon we've seen is around, depending on the doping, et cetera, of the order of 1,000, say, okay? While the mobility of electrons in silicon dioxide is only maybe 1 or 2. Same in hafnium oxide, it's very, very low because these dielectrics are amorphous materials, and typically in amorphous systems, you have low mobilities, okay? Because the mobilities are so low, when these electrons tunnel into the material, they gain kinetic energy, they can cause impact ionization within the oxide, exciting electrons from the valence band of the oxide to the conduction band. In the process, they leave behind holes, and you create secondary electrons. Some of these holes can get trapped at defects in the oxide. That changes the electric field profile. You see that the electric field is becoming higher because of the trapped oxide, where you have field lines from these trapped holes to the gate electrode. So this turns out to become a positive feedback mechanism. And at some point, the dielectric catastrophically breaks down by a process known as time-dependent dielectric breakdown, which is one of the main ways by which semiconductor chips fail after maybe, hopefully, after 10 years or so, okay? So it's a long-term reliability problem. Any questions? Okay, so let's set aside MOS capacitors and now jump into MOSFETs. So now we are looking at the three-terminal behavior of the MOSFET, or strictly speaking, a four-terminal behavior.
Professor?
Yeah.
I was just curious, so like if you have like a spacecraft, for example, that's out in space for like a decade or two that has like semiconductors, is it usually hindered by that limit, or are they able to do something like advanced with it to make it last longer?
Yes, very good question. In fact, in outer space, things are even worse because the chips are going to be subjected to high energy cosmic rays, okay? On the Earth also we have cosmic rays, but thankfully the atmosphere blocks out 99.9% of the cosmic rays, okay? Cosmic rays are high energy particles like alpha particles and gamma rays and things like that, all of which can cause such charge trapping in ICs and therefore can cause them to fail. So it's a huge problem that NASA faces. So when you send ICs into outer space, they're designed specially, and those are known as rad-hard devices, meaning that they're hardened against radiation, such as cosmic rays, and the process they're also hardened against damage due to, say, time-dependent dielectric breakdown and other kinds of damage that I'll discuss maybe on Wednesday. Okay, it's an important question. So to answer your question about what they do, they'll do things like, they'll make the oxide thickness thicker than you have in the oxides in your Pentium computer chip, for example, okay? So you may sacrifice a little bit of performance in order to gain in the area of reliability, okay? And there's other things that are done also that we don't have time to get into, but that's an important point. Okay, so we are looking at the MOSFET.
I read that the Voyager spacecraft has been running 35 years.
Yep, yeah.
Continuously.
Amazing, yeah. Now with the Voyager, it turns out it's so old that I believe the chips on that device are not MOS devices. I could be wrong, but I think a lot of them are bipolar devices, which we'll be talking about next week. And BJTs don't suffer from the same problem as MOSFETs because they don't have a gate oxide, okay? I think a lot of those Voyager chips are pre-MOS technology, okay? But if they use MOS, once again, they would make the oxides much thicker so that they'll be radiation hardened, yeah. But, typical computer chips, terrestrial applications, generally speaking, they'll guarantee a reliability of about 10 years or so, okay? And companies count on the fact that, consumers typically don't even keep their electronics for 10 years. They get rid of them after a few years. Unless you're like me, I still have my old VCRs and videotapes, and my children make fun of me. All right, so we're looking at the MOSFET now, which is a three-terminal device where you have a source, drain, and gate. But as I've told you, it really is it has a fourth terminal, which is a substrate, okay? Now, for this MOSFET, we'll always have to reference the voltages to one terminal, and the convention is to assume that the source voltage is the ground voltage. And generally speaking, we'll also assume that the substrate is grounded, okay? Though sometimes we can apply a substrate bias, and that gives rise to this dependence of threshold voltage on substrate bias, as we mentioned last week, okay? To the gate, we'll apply a gate voltage, and then to the drain, we apply drain voltage, assuming this is an N-channel device. So this will be N plus source drains, and then it's a P-type channel, and you have an N-type inversion region, okay? So I'm interested in calculating the current voltage behavior through this MOSFET, okay? A blown-up version of the channel region is shown in this figure over here. So imagine the source would be over here, drain would be over there. And as you can see, because I've applied a drain voltage, and this current flowing from the grounded source to the drain, the potential along the channel, that's my x-axis, rises from 0 at the grounded source up to VD. But unlike in a resistor, it doesn't increase linearly. it curves up. Okay, why? Because you can see that as the channel potential rises, the voltage difference between the gate and the channel is different at different points. At the source end, it's VG minus 0. At the drain end, it's VG minus VD. Well, somewhere in the middle of the channel, it'll be VG minus VX, whatever the channel potential is at that point in the channel, okay? And as VX rises, the voltage difference between the gate and the channel goes down, and therefore there's less effective gate voltage available to invert the channel, and that's what causes this inversion region to gradually get pinched off, okay? Now, because the inversion region gets pinched off, and you have to have the same current across every cross section to satisfy KCL, the only way that can happen is the electric field along the channel has to gradually increase from the source end to the drain end to compensate for the pinching of this inversion region, okay? And that increasing electric field is reflected by this Vx curve curving upwards, okay? Because the electric field at any point is given by the slope minus dV dx, and the slope increases, okay? So the slope or the electric field will self-adjust to make sure that the product of the electric field and the available carrier concentration gives you the same current at any cross section. Now, to analyze this, we'll first start off with a simpler device, which is a simple ohmic resistor shown on the left, okay? And I'll write the current voltage characteristics in a funny way so that you can then make the correspondence to the MOSFET, okay? So in this resistor, suppose I apply a voltage VD, and I'm calling it VD to kind of correspond to the MOSFET where the applied voltage is VD, and the current flowing is ID. That's, of course, given by the voltage divided by the resistance of the resistor. That's Ohm's law, okay? Now, resistance R, you remember, is given by rho, the resistivity, times the length of the resistor L, divided by the cross-sectional area. In this case, the cross-sectional area is Z in this direction. So Z is the direction perpendicular to the plane of the board, okay? Times Y, Y is the thickness of the resistor. So that will be the thickness of this inversion region over here, okay? So that's given by Z, Y, okay? As shown over here. Now, rho, the resistivity, is given by 1 over conductivity, which is Q mu N. Mu is the mobility, N is the carrier concentration per unit volume, okay? So if I plug that in for the resistivity over here, this Q mu N appears in the numerator as shown, okay? And you get a current which is given by this, okay? So I'm writing it in a very funny sort of way. Now I look at the terms differently. So over here, for example, the mu, I pull it out over here and I write it as mu times VD over L. But what is VD over L? VD is the voltage, L is the length. So VD over L is nothing but the electric field in the resistor in this direction, right? And mobility times electric field we know is drift velocity, okay? Of course, only as long as I'm in the ohmic region. So if I was to plot the drift velocity as a function of E, we have seen that in the ohmic region is given by mu times E, and that's what I'm assuming over here. So I'm assuming low electric fields in the ohmic region. But remember, in the pinch-off region where the electric field can be high, you'll ultimately saturate at V sat, and that's what gives rise to your saturation drain current, ID sat. Okay, so let's look at the other term. So mu times this is my mobility times electric field in the ohmic region, or the drift velocity. Now let's look at this term. What is this? It's electron charge Q times N, which is the number density per centimeter cubed carrier concentration, times Y. Okay, so what will be the units of this? The stuff in the parentheses. It will have units of coulombs per centimeter square. Why? Well, N has units of number per centimeter cubed times Y, which is in centimeter. That'll give you number of electrons per centimeter square if I look at the resistor from the top, okay? So it's the electrons per unit area by integrating as a function of the depth of the resistor, okay? And then to get charge, you have to multiply by the charge of the electron, okay? Like I said, I'm writing the simple resistor formula in a very funny way so that we can make the correspondence to the MOSFET in a second, okay? So the point is, the current is proportional to the width of the resistor, and it makes sense, right? The wider the device, more the current, times the charge per unit area, looking at it from the top, times the drift velocity, which is mobility times electric field, if the electric field was low enough. If the electric field was high, mu times this electric field has to be replaced by V sat. Okay? And that's what we'll have to do in a short channel MOSFET. We'll see later on. Everybody with me? All right. So now let's make the correspondence to the MOSFET. Okay. So what I need to do is I have to find out the electric field along the channel, and that is nothing but minus dV dx along the channel times the mobility of the carriers. We'll see that's typically going to be lower than the mobility that we have seen in the bulk of the semiconductor. It's known as the surface channel mobility. Now, mobility, remember, is governed by scattering. Scattering is anything that is a deviation from perfect periodicity. Okay. In this scenario, you'll have an additional source of scattering, which is due to microscopic roughness between this gate dielectric and the silicon channel. Okay. And that's why the mobility of carriers in the inversion region will be lower than what you have in the bulk semiconductors. On top of that, of course, you got the phonon scattering and the ionized impurity scattering that we've talked about. The hard part is this term in the parentheses, which is charge per unit area. How do I do that? Well, I have to look at this MOS capacitor and integrate the charge distribution as a function of depth in the inversion region, which of course now depends on this position X, right? The more you go to the right, that charge, integrated charge will be less, okay? How do I get that? Well, to do that, you have to look at the capacitance voltage behavior of this MOS structure, which we discussed last week. Let me refresh your memory about that. So if it's a p-type silicon channel, if I have to plot the oxide capacitance as a function of gate voltage, we know for negative gate biases, you get the accumulation region. You attract holes. There's no inversion region, no depletion region. And you get a fixed parallel plate capacitor given by, sorry, this is gate. So this is Cox or Ci. But then as the gate voltage becomes more and more positive, you start pushing away the holes, you start forming a depletion region, the depletion region expands more and more. You now get a series combination of two capacitors. One is a Cox, which is fixed, and in series with the C depletion, which is C depletion, of course, is given by epsilon silicon divided by the depletion width, which is voltage dependent. Therefore, C depletion is voltage dependent. As the depletion width expands, this goes down, and therefore the series combination of the capacitance goes down. That happens until you get the maximum depletion width corresponding to a band bending of 2 phi f. Phi f, remember, is a Fermi potential. It's given by kT over q log of Na over Ni. That's the difference between the Fermi level and the mid-cap level. 2 phi f is the maximum band bending, where you now get strong inversion, and that point is known as your threshold voltage. Once you reach threshold, the capacitance goes up very steeply, and you're back to Cox again. Okay, so my BT is not exactly the minimum, but approximately at the minimum. Okay, and this slope is very, very steep. All right, and suppose I've applied a gate voltage of this much. So I have to figure out how much inversion charge is formed at this gate voltage above this threshold voltage, right? When I'm at the threshold voltage, the inversion charge is still pretty much close to zero, right? Because I'm barely at the onset of strong inversion. It's only when I go above threshold voltage, I start pumping in more and more inversion charges. How do I calculate that? Well, remember we said that these capacitors, being voltage dependent capacitors, you cannot write C, look for some space over here. You cannot write C as Q over V. What do you have to write it as? dq over dV, right? Just like if I have a nonlinear resistor, you can't write resistance as V over R, you have to write it as dV over dr, sorry, dV over di, and so on and so forth, okay? It's just a differential form of it. So if that's the case, and I have a voltage dependent capacitance, oxide gate capacitance, okay? I can integrate both sides. So now inversion charge would be nothing but the voltage dependent capacitance dV, right? Integrated from VT to whatever the gate voltage is, right? So that's my gate capacitance, C, plotted as a function of voltage, right? And charge in the inversion region, Q inversion, will be the integral, just by inverting this, it'll be integral C dV, right? Because C is equal to dq dV, therefore Q would be integral of C dV. You guys with me? But what is integral of C dV corresponding to this curve? It's nothing but the area under this curve, right? Now, approximately, you can write the area under this curve as C oxide or Ci, C insulator. I've been using C oxide or C insulator interchangeably. If the insulator happens to be an oxide, we sometimes call it a C oxide, but in general, it's a C insulator, Ci, okay? Times Vg minus Vt, right? Vg minus Vt is this base, and C ox or Ci is the height of this curve, right? Now, it's not an exact rectangle, but it's pretty close, because once you hit inversion, this curve goes up very, very steeply. Okay? So that's why you can write down this inversion charge, Qn, as minus Ci. The minus sign is simply because of the sign convention that you've chosen. I'm looking at electrons in this case, which are negative charged, okay? The important point is it's capacitance of the insulator, not the overall capacitance. It's the capacitance of the insulator, Cox or Ci, times Vg minus Vt. Vg minus Vt. Now I'm writing Vt as flat band voltage plus surface potential, which at inversion, surface potential is equal to 2 phi f, minus depletion charge over Ci. You can look back at your notes from last week, and that is your expression for your Vt. Okay, so that's Vg minus Vt. But there's one more catch, okay? And that last catch is, this is not a band bending of 2 phi f at every point in the channel, right? Because as I said, the channel potential rises from 0 to some Vx in the middle, and then Vd at this end of the channel, right? So you have to add the channel potential phi s to the additional voltage drop Vx because of the current flowing in the channel. So wherever I have phi s, you replace that by 2 phi f at inversion plus Vx, okay? Similarly, in the depletion region, depletion charge, if you look back at your notes, you had 2 phi f before, but now if you replace that by 2 phi f plus Vx, okay? And since Vx rises from the source end to the drain end, you'll see clearly that the depletion charge will keep expanding from the source to the drain end as a function of depth, okay? And the inversion charge will keep decreasing, as shown by this cartoon view over here, okay? And because this inversion charge decreases, the electric field has to increase to make sure that the product of the two stays the same, okay? All right, so now hopefully that you understand that, okay? You can calculate the current as shown over here. Now to do so, I'm first making a simplifying approximation. I'll ignore the variation of the depletion charge, which is this term over here, as a function of x. So I'll initially ignore this Vx term over here. Now that's an approximation which works reasonably well if the drain voltages that you apply are small. So it applies well as long as you're in the so-called linear region of the Mosfet, okay? So I'm looking ahead, so that's my output characteristics. If you remember the JFET expression, we said that that's your VD sat, okay? This part is known as the linear region, and this part is known as the saturation region, where you get ID sat, okay? Once the channel has been pinched off. So I'm looking at low drain voltages, okay, in the linear region. And if it's a low drain voltage, you can kind of ignore the Vx. The maximum value of that would be Vd in comparison with the 2 phi f. That's an approximation, okay? Let's make that approximation first. So then you can write this as Vg minus Vt, which is V flat band plus 2 phi f plus depletion charge over Ci. And then, of course, you have the Vx over here. I'm not ignoring the Vx in this linear term. I'm only ignoring it in the square root term over here, all right? So then you can write down the drain current using this as a guide as the width of the device in the direction perpendicular plane of the board, which I call Z, times inversion charge per unit area, which is this term in the parenthesis Qn, and I've gotten an expression for the Qn over here. And then mobility times electric field, where electric field is dVx dx, but I bring the dx over to the left-hand side, and I integrate both sides, okay? The left-hand side I integrate from 0, which is the source end, to L, which is the drain end of the channel, ID dx. Now, how does ID vary as a function of position in the channel? According to KCL, it has to be constant, right? You have to have the same current everywhere. So the left-hand side is nothing but ID times L. On the right-hand side, you have to integrate with respect to Vx, the channel potential, between 0, which is the grounded source, to Vd, which is the drain potential. You have to integrate the stuff in the brackets over here, right? So that's Vg minus Vt minus Vx. Now, what do I get if we integrate that? Well, this term is a constant, so that'll give you Vg minus Vt times Vx between the limits, of course, of 0 to Vd. So that'll give you this first term over here. And this integral of Vx dVx will give you half Vx squared, so minus half Vx squared, once again between the limits of 0 to Vd. So that'll give you this final term over here, okay? So that is my expression for the current, drain current as a function of the gate voltage and drain voltage in a MOSFET. It's an approximation for low drain biases where you could ignore this quadratic term over here, okay? That is a form of the expression that we'll be using in our class to solve homework problems. But just for the sake of completeness, what if you did not ignore that Vx term in the depletion charge, okay? It's quite straightforward still. It's just that the expressions look a little bit messy. That solution is shown over here, okay? So now you get the original terms, but now you have to also integrate this term over here. What is that? Well, it'll be integral of 2 phi f plus Vx, integral of that with respect to Vx, right? So I'm integrating this with respect to Vx. What will I get? Well, if I integrate square root of x dx, what do I get? I get x to the power 3 halves, right? So that's what you end up getting over here. So you get something to the power 3 halves between the limits of 0 at the grounded source. So that thus gives me 2 phi f to the power 3 halves. And then at the drain end, Vx is equal to Vd. So that gives you Vd plus 2 phi f raised to the power 3 halves, okay? So that's a more accurate version of the current voltage characteristics. While this is a simplified version where I ignored the dependency of the depletion charge on channel position, okay? Now, interesting enough, you can go back from this full-blown version back to this simplified version if you make a Taylor series expansion for low Vd, okay? So if I make a Taylor expansion, you'll see that this simplifies to this, and that makes perfect sense, right? Because for a Taylor expansion for low Vd, I'm once again ignoring this depletion charge dependency on position x or on Vx, right? So if I ignore that by making a Taylor expansion for low Vd, I better get back the original expression where I ignored the variation of depletion charge with Vx to begin with, okay? For our class, we'll use the simplified version for all our homework problems or exam problems. While if you take a graduate class, you might sometimes have to use this full-blown version over here, okay? All right, so using this as our starting point, let's see what kind of things we can glean from that, okay? Now, a couple of words of caution, okay? So in our textbook, we call the width of the device. The width of the device is the direction perpendicular to the plane of the board. So that's this direction. We call that Z because in our axis, that was the Z axis, okay? Now, in most other textbooks or in the literature, people call that direction W because it's the width of the device. So if you read many other papers or textbooks, very often instead of Z, they'll call that W, okay? Now, we chose not to call it W in our textbook because we reserved W for the depletion width over here. Okay, so we didn't want students to get confused. But having said that, because most other papers tend to call the width of the device W, as well as the depletion width, maybe a different font of W, I'll sometimes also do that, okay? So I'll use the term Z or W interchangeably for width. And similarly, I'll use the term CI or COX interchangeably for the oxide capacitance, okay? So don't get confused by that. Okay, so let's see what we can get from these current voltage characteristics, okay? Some terminology. This prefactor over here is sometimes written as a new term, Kn, which is called the gain of the device. It will become clear in a second why that's a gain, okay? You can then define the saturation drain voltage. That's the drain voltage at which the current saturates. So that is this dotted line over here. That works out to VG, whatever gate voltage I've applied, minus VT. Why is that? Well, if my gate voltage is VG and my drain voltage VD has risen to VG minus VT, what would be the voltage difference between the gate and the channel at different locations? Well, the voltage difference between the gate and the channel at the source end would be VG minus 0 because the source is grounded, right? At some point X, it will be VG minus VX. And at the drain end, it will be VG minus VD, right? And if I have increased VD to this value, the voltage difference would be VG minus VG minus VT, which works out to VT, right? So that means that when the drain voltage is equal to VD sat, at the drain end, the voltage difference is just equal to the threshold voltage, which is barely the point where I start forming the inversion region, right? And that's where the point where the channel inversion region will get pinched off. And beyond that point, the drain current doesn't increase much, okay? It saturates at VD sat, okay? In fact, under those conditions, the electric field in the pinch-off region is so high that the carriers will essentially travel at VSAT. So I'm not in the ohmic region anymore. You'll travel at the saturation drift velocity. And that's one of the reasons also why the current saturates, okay? All right, so VD sat is equal to VG minus VT, okay? Now you can get the corresponding value of ID sat by simply then plugging in the value of VD sat over here, okay? If you do that, what do I get? Well, I get from the first term, VG minus VT times VD sat, which is equal to VG minus VT, or VG minus VT whole square, minus half VG minus VT whole square, right? The factor of half cancels out, so that's why I get the factor of 2 over here, and you get this, where VD sat is VG minus VT. So VD sat squared is VG minus VT squared. What does that mean? If I look at the output characteristics, where I plot output current as a function of the output drain bias, you get a family of curves which are not equispaced, okay? These curves of ID sat will be this gain term Kn that I mentioned times VG minus VT whole square divided by a factor of 2. What does it tell me? It tells me that this drain current depends on the gate voltage, but is independent of the drain voltage. The current saturates, okay? Which is absolutely wonderful from a circuit point of view, because what does it tell me about my output impedance? Any guesses? Impedance is defined by change of voltage divided by change of current, right? Impedance is the general form of resistance, if it's frequency dependent, okay? Let's call this resistance, output resistance. That's change of voltage divided by change of current. Well, I have a certain change of output voltage. What is my change of current? 0. Therefore, the output impedance is infinity, right? Or close to infinity. Similarly, the gate impedance, hopefully there's not much tunneling leakage current. So the gate impedance is also, gate resistance is also very, very large, close to infinity. And that's what makes a MOSFET so attractive for large scale ICs. You consume very little power because you have a high input impedance and high output impedance, okay? Everything is capacitively coupled, all right? One bad thing, however, is this output characteristics depend quadratically on the input voltage, okay? And that then gives you nonlinearities of gain between the input signal and the output signal. Now, fortunately, as we'll discuss on Wednesday, when we have short channel MOSFETs, as we discussed briefly with short channel MESFETs, the curves tend to become equispaced as a function of VG. So you actually get a linear gain for short channel devices, but let's hold off on that till Wednesday. Okay, now once you have the IV characteristics, you can define circuit parameters that I'm sure you studied in 438, things like conductance, okay? Linear conductance in the linear region, okay? So how do you get that? Well, conductance is defined as not I over V, but delta ID over delta VD, okay? This is just simple calculus, okay? You can take this expression in the linear region, okay? Linear meaning low drain voltages, not VD sat, much less than VD sat, and simply take the derivative with respect to VD. You end up getting this. On the other hand, saturation conductance is 0 because we just saw that saturation impedance is infinity. Okay. You can also define terms called transconductance, which is another way of calling it gain. What does transconductance mean? In the case of regular conductance, you're looking at output current as a function of output voltage. In transconductance, on the other hand, you're looking at output current as a function of input gate voltage. Okay. You can look at the expression over here, and now you have to take the derivative with respect to VG, okay, and you end up getting this. Okay. Saturation transconductance, you look at the saturation drain current, which is VG minus VT whole square divided by 2, and take the derivative with respect to VG. So you can get all kinds of circuit parameters, okay? Now these kind of correspond to gain because I'm looking at change of output something as a function of input something. Now it's not voltage gain or current gain, but it's called transconductance. Very, very, very important parameter. Okay. Any questions? So this derivation of the IV characteristics, you ought to try to go through again to make sure that you understand all the steps, because I will give you exam problems, final exam problems where you have to solve current voltage characteristics of MOSFETs. I'll give you problems dealing with capacitance voltage characteristics of MOSFETs, and I will give you problems dealing with current voltage characteristics. And I can guarantee you, this will be an open book exam. I can guarantee you it will not be simple plug and play. Okay, you might think that, oh, I'll have the formula in front of me, be very straightforward. You don't. You really have to understand the physics, because there'll be, tricks in the homework problem, in the exam problem. Okay, so study this very, very carefully. Make sure that you can derive these expressions over here. You can look at the CV behavior, see how the two are connected. Okay, make sure that you understand MOSFET IV very well. This is a key part of the course. Okay, that was sort of the hard part. The rest will go relatively easily. Over here, we are looking at the N-channel MOSFET that I've been talking about so far, where you have N plus source drains and a P-type channel. So now to connect the source to the drain, you have to apply a high enough gate voltage, higher than the threshold voltage, okay? So that you form an inversion region of electrons connecting the source to the drain. And if you do that, if you apply now a drain voltage, it's like a ohmic resistor initially. Okay, you get a linear dependence of drain current with drain voltage, where the slope depends on the gate voltage, right? Higher the gate voltage, more inversion charges, therefore the channel becomes more conductive, and the slope is steeper, okay? Meaning it's more conductive or less resistive, okay? But then, of course, as you increase the drain voltage, the channel gradually gets thinner and thinner near the drain end. And at VD sat, it gets completely pinched off. And then beyond that point, you have to pull out carriers from this inversion region across this pinch off region into the drain, okay? As Branch asked a good question last time, even though it's a pinched off region, which is a depletion region, carriers can still flow across that, okay? So depletion only means that if I didn't have a drain bias, that region would be depleted of carriers, okay? But just as in the case of a p-n junction, electrons and holes can flow across the depletion region of the p-n junction. Depletion region does not mean that it blocks current flow, okay? It's just that the carriers will flow very, very quickly across that, typically with the saturation drift velocity. Okay, for an N-channel MOSFET, you apply positive drain voltages, source is grounded, so that you pull the electrons this way. But if the electrons flow this way, which way does the current flow? Well, the drain current would be this way, right? So you have a positive drain current, positive drain voltage, and you apply positive gate biases, okay? And generally speaking, you design the thing to have a VT, which is positive. Typical VTs would be of the order of 0.6, 0.7 volts. Okay, that's quite common. I'll tell you why later on today. So that means that if my gate voltage is 0, that's less than the VT, and then the transistor will be turned off. Okay, in this case, the gate threshold voltage is slightly below 3 volts. Okay, it's maybe, I don't know, 2.5 volts. So below that, you see that the drain current is 0. Okay, so these are known as normally off transistors. Okay, which are also known as enhancement mode devices. Okay, on the other hand, you could have made a MOSFET where this channel region, instead of being p-type, was doped n-type to begin with, not because of the gate bias, but by doping. Okay, it's kind of like your JFET structure where the channel was already pre-doped. Okay, what's going to happen then? Well, if the channel is already doped n-type, I don't need to apply a gate voltage to form the channel, right? As soon as I apply a drain voltage, electrons will flow. So this is known as a normally on transistor. These are also sometimes called depletion mode transistors, okay? Because you now, to turn the transistor off, you'd have to apply a negative voltage to turn the transistor off, right? So now you'd have a VT which is negative. Maybe it would be minus 1 volt, for example, okay? So in that case, if the gate voltage is 0, that's more positive than the minus 1 volt VT, meaning that the transistor is on, okay? Generally speaking, you don't like that, okay? Typically, people like transistors where if the input voltage was 0, you want the transistors to be off. So in most cases, you want these so-called enhancement mode transistors, where for an N-channel device, the VTs are positive. You want normally off devices, okay? And all of this is for an N-channel device. You can also have P-channel devices where you flip all the polarities. Now you have a P plus source, P plus drain made in an N-type channel, okay? And let's see what the polarities would be. Now, you'd have to apply a negative drain bias, which is shown over here. VD is negative, to attract holes from the source to the drain, okay? And now the current, the holes would flow this way, and because holes have a positive charge, ID is this way, right? In the N channel, the electrons flow this way, but the ID goes into the device. And the sign convention is when the current goes into the device, you call that a positive drain current. On the other hand, when the current is flowing out of the device, to make it a consistent convention, these currents are considered to be negative, okay? So in a P channel, you have a negative drain voltage and this current flowing out because of the drains coming out of the holes coming out of the drain. The sign convention is that's also considered to be a negative current, okay? And under these conditions, you typically design the thing to have a VT which is negative, okay? Once again, making it a normally off device, okay? So what do you have to do then? Now you have to make the gate voltage more negative than whatever the negative VT is to induce holes in the channel, okay? On the other hand, if the gate voltage is 0, that's not more negative than this negative VT, the transistor will be turned off, okay? All right, so that's kind of shown over here for this sort of P-channel MOSFET, okay? So if my gate voltage, if my threshold voltage is negative, those are called the enhancement mode devices. But if in the P-channel, the threshold voltage happened to be positive, you now would have to apply, the transistor would be normally on, right, at 0 gate voltage. And then you'd have to apply a positive gate voltage to push those holes away, the implanted holes, away from the channel to turn the transistor off. Generally speaking, that's not desirable. Enhancement mode is typically what's used, okay? These are used rarely in niche circuit applications like resistive resistors and things like that. Now, in a typical IC, we'll see on Wednesday or maybe on maybe next week, you generally have N-channel devices and P-channel devices work hand in hand. And if you do that, those are called complementary MOS devices, or CMOS. And that's a beautiful circuit architecture, because you'll find that you can design your Boolean gates like inverters or NAND or NOR, where you always have an N channel and the P channel work hand in hand, such that when the N channel is turned on, the P channel will be turned off, or vice versa. Okay. Now, because one of these two transistors is always in the off state, CMOS consumes very, very low levels of power. Okay. And that's really behind the fact that you can, integrate literally billions of these devices, transistors, in your computer microprocessor chips or your cell phones and things like that. Okay, because it consumes so low power. That's especially important for mobile applications, like in your cell phones. Otherwise, your battery would run out in maybe a few minutes instead of lasting a day. Okay, we'll talk about that probably next week. Any questions? All right, this slide shows what are called transfer characteristics. The previous curves are called output characteristics, because I'm plotting output current, drain current, as a function of output drain bias. Okay. On the other hand, these curves are called transfer characteristics, because I'm plotting output drain current, not as a function of output drain bias, but input gate voltage. Okay. Now let's see what those curves would look like. Well, you can look at the linear region characteristics, where for low drain biases, I've ignored the minus half VD squared term that I had. Okay. If you look at the previous expression, you had a minus half VD squared. I'm kind of ignoring that for a second. And let's see what I get. Well, if I plot ID as a function of VG, this expression that I showed a while back. Okay, so here I'm momentarily ignoring the half VD squared term for assumed low drain biases. Okay, if the drain bias VD is very, very small, suppose VD was 0.1 volt, okay, then VD squared would be 0.01, and kind of ignore the quadratic term. And that's what I'm showing in the simplified version. Okay, so you see that if I plot output current as a function of input gate voltage, I should get a straight line whose slope would depend on this prefactor. Okay, and that's what I call K, or the gain of the device. Why is it called gain? It's called the gain because it's sort of change of an output characteristic, my output drain current, as a function of an input signal, the input gate voltage. Okay, so it's not voltage or current gain, because for voltage gain, AV, it would be delta V out over delta V in. Similarly, current gain would be delta current out over current gain, current in. But it's not those. This is called transconductance, because I'm looking at change of output drain current as a function of change of input gate voltage. Okay, so that's why it's called transconductance. Okay, and this is also sometimes indicated as GM. Okay, GM, change of output drain current as a function of input gate voltage. Okay, so if I take the derivative, I get this plot. Okay, so I take the slopes at different points. Okay, and I get the transconductance as a function of gate voltage. So what you see clearly below threshold. Okay, so this curve, by the way, it will be more or less a linear curve whose intercept will be the threshold voltage, right? Because when VG equals VT, the current goes to 0, right? So this curve predicts that the current will abruptly go to 0 at VT. Okay, and that's one way you can measure experimentally the threshold voltage of a transistor. So you plot the linear region characteristics as a function of gate voltage. You take the extrapolation, and where it intersects is your threshold voltage. It's a way of experimentally measuring it. Okay. Now, in practice, you'll find that the current in a transistor doesn't go abruptly to 0. There'll be some current below that. It'll gradually go down to 0. That current, we'll discuss later on, is known as your sub-threshold current. And the rate at which that current changes with gate voltage gives you something called the sub-threshold slope. Very, very important parameter of a MOSFET, because it tells you how effective the MOSFET is as a switch to go from the off state to the on state, or on to off, right? In an ideal case, you want the transition to be as abrupt as possible, but the physics tells you it'll never be perfectly abrupt. In fact, we'll see it's an exponential function, and that gives you the so-called sub-threshold slope. It's a hallmark of how good it is as a switch, all right? Now, above threshold behavior is what I'm focusing on for right now, okay? And you have to look at what I said is a transconductance, change of output current as a function of change of input voltage, okay? And you take the slopes at different points. Here, the slope would be 0. And then the slope gradually increases. That's the point of maximum slope. So that's my GM max. But then you'll find that although this curve predicts a linear characteristic, a practical device will have the curve bending downwards. So it don't be this dotted line as predicted by this equation, the curve as shown over here. Now, the question, of course, is why. The reason it slopes is because this term mu n, this channel mobility term, we'll find decreases with increasing gate voltage. I'll tell you the reasons why in a second, but the basic reason is as the gate voltage increases, the electric field in this direction keeps increasing. These electrons are drawn more and more closely to this interface where we have microscopic atomic roughness, as I mentioned at the beginning of this lecture today. Okay, remember we said that we have atomistic roughness, and anytime I have a deviation from periodicity, that causes scattering, and that's what causes the mobility of the carriers in the inversion region decrease as the gate voltage increases, as this electric field increases, okay? One visual way of thinking of it is you're sort of moving this electron gas across a rough surface. Kind of think of this as sandpaper, right? And if you move across sandpaper gently, you'll feel a certain amount of friction. But if you sort of press your hand tightly against the sandpaper and try to move, it's harder to move, right? And that's kind of what it is, okay? It's kind of like rough sandpaper. Higher the gate voltage, I'm pushing the electrons closer and closer to that rough sandpaper surface, and it becomes harder and harder to move the electrons from the source to the drain, okay? It's sort of a colorful way of looking at the physics. The other reason the curve bends over, we'll see also later on, is because of source-drain series resistance, okay? The origin of this is the fact that in the source and the drain, you have some series resistance, which is called RS and RD. So then, when I apply a drain voltage, and there's more and more drain current flowing, some voltage will be wasted, which would be ID times RS over here and ID times RD over here, so that the actual voltage applied across the transistor, which I call VD prime, say, would be the external VD minus ID times RS plus RD, which sometimes is called RSD, okay? So as a result, as the gate voltage goes up and the drain current goes up, there's more and more voltage wasted across the source and the drain regions, and the voltage available, the drain voltage available for the actual transistor itself goes down. That's why the curve bends over, okay? That hopefully will immediately tell you why it's so important to have a low source drain series resistance, because you don't want to waste a lot of the applied external voltage across this parasitic source drain resistance. We'll see later on how that is achieved in practice.
The top curve suggests that there should be a flat region, and the bottom curve, it seems, isn't that correct?
So which curve are you referring to here?
The top left curve looks like there should be a flat region in the slope that the bottom left curve does not show.
I'm not sure I fully and so as the curve bends over, the slope decreases, right? And that's what's shown over here. Is that what you're referring to?
Where the slope Kn linear is shown.
Yes.
It seems like that should be pretty flat for at least a short period.
Yeah, yeah. So I mean, yeah. So you say if it's flat, yeah. So there may be a range where it's kind of flat. Yeah, this is just a cartoon view. So you're saying that it should kind of constant for a while and then go down. Is that what you're saying?
Yes.
Yeah. But you know, so generally what happens is that region where it's constant slope is typically a small range of gate voltages. So you get the maximum slope where you get the point of inflection of the curve. Okay. But you know, there could be a certain region that's kind of flat here, right? All right, you can also look at these transfer characteristics in the saturation region. So here I was looking at in the linear region. On the right-hand side, I'm looking at in the saturation region. So linear region is this part, but the channel wasn't pinched off. Saturation is the right-hand side of the curve, okay? Now on the right-hand side, we saw that the ID sat scales as VG minus VT whole square divided by 2 times this prefactor, mu C ox W over L. So if that's the case, if I plot ID as a function of VG, I'll get a parabolic dependency, okay? So instead what's done is you take the square root of both sides. If you take the square root of this, of the drain current, now you get something varying as VG. So in the saturation region, you have to plot square root of the saturation current as a function of VG. And if you do that, once again, you get a more or less straight line, and the extrapolated version will give you the threshold voltage. Now, based on the discussion so far, there's no reason to expect that this measurement of the VT should be any different from this measurement of this VT, right? And that's true if it's a long channel device. However, we'll see on Wednesday that for short channel devices, by short channel, I mean channel lengths less than maybe half a micron or so, there's all kinds of secondary effects, which are generally known as short channel behavior, which will cause this VT measured in the saturation region to be lower than this VT measured in the linear region. Okay, you get two-dimensional electric field profiles, you have to solve the Poisson equation, and you get effects known as brain-induced barrier lowering, but I'll discuss those on Wednesday. Okay. All right. The thing that I want to elaborate on is what I've already mentioned, is this business of effective channel mobility. Okay. This effective mobility is the fact that, as I said, these electrons in the inversion region or these holes in the PMOS, as they travel from the source to the drain, not only do they see the usual sorts of scatter that you have in bulk, which are phonons or lattice vibrations or ionized impurities, but now you have additional sources of scattering because you have additional sources of deviations from perfect periodicity because of this atomistic scale roughness between the amorphous gate oxide and the single crystal substrate, okay? And then that causes this channel mobility to be lower than in the bulk of the semiconductor. Furthermore, as I mentioned, the higher the gate voltage, you draw these electrons or holes closer to that rough surface, and there's more and more scattering, okay? So that's the story of the next couple of slides. Now, this effective mobility in the channel can be written using Mathiassen's rule that I had mentioned in chapter 3 by taking the harmonic mean of these individual components. You do Coulomb scattering, phonon scattering, carrier scattering, and now this additional thing is called surface roughness scattering. Okay? Because this surface is not going to be perfectly smooth. If you were to zoom in and take a picture of that, and these days you can actually do that using cross-sectional, very high resolution micrographs using what is called transmission electron microscopy, you'll see that you transition from a nice single crystal silicon structure to an amorphous oxide or hafnium dioxide structure where you have a lot of dangling bonds, rough interfaces, and so on and so forth, okay? That causes this additional scattering, which is called surface roughness scattering. Now, the question, of course, is why do I combine mobilities in this funny way? Just to refresh your memory, we said that mobility is given by charge of the electron times time between collisions divided by the conductivity effective mass. Remember that? With the time between collisions, if I take the reciprocal of that, that gives you what is called the scattering rate. S, scattering rate, right? Clearly, if I have a higher scattering rate, the time between collisions would go down, right? There's an inverse dependency. So the basis behind Mathiassen's rule is, he said that if you have different scattering mechanisms, you know, ionized impurity, Coulomb scattering, phonon, etc., you simply add up the scattering rates. You could say phonons plus scattering rate due to Coulomb scattering or ionized impurity scattering, so on and so forth, okay? So then you can write down individual mobility terms. So you have a mobility due to phonons, for example, okay? Now the reciprocal of that would be 1 over tau, right? So when I take 1 over mu phonon, it's basically proportional to the phonon scattering rate, okay? That's proportional to the ionized impurity scattering rate, and so on and so forth. So essentially what I'm doing is I'm adding up all the scattering rates to get the total scattering rate, and the reciprocal of that will give you the overall mobility, right? So that's why you get 1 over mu overall equals 1 over mu due to scattering mechanism 1 plus mu 2, and so on and so forth, all right? Now this channel mobility as a function of this vertical electric field in this direction. That's what I'm calling effective transverse field, okay? Is shown over here. This is actual experimental data for different temperatures. I'll explain in a second what this business of effective electric field is, okay? So it's some sort of an average electric field in the inversion region, roughly measured in the middle of this inversion layer, okay? My source is over here, drain is over there. So I have a certain inversion layer. The electric field decreases as a function of depth, it turns out. If I take the average, that's what I mean by the effective transverse field. So people discovered back in the late 70s that regardless of how you make your MOSFETs, regardless of who made the MOSFET, Intel or Samsung or AMD, TI, whoever, if you replotted the mobility data in all these MOSFETs, okay, doesn't matter whether it's a 10 micron channel length, a certain channel doping, TI makes a 1 micron channel length, the different channel doping, different oxide thickness, you have all these variations, right? But if you replot the data as a function of this average electric field, and I'll have the expression for that in the next slide, all the mobility data, say at room temperature, lie on a single universal curve. And when people made that observation, I mean, that was earth-shattering, right? I mean, because, you know, one would think that why the heck would transistors made by different processes, different companies, different oxide thickness, doping, have this universal mobility dependence, right? But they do if you plot it as a function of this effective transverse field. The only dependency is now on temperature. Any guesses as to why the mobility, the effective mobility in the channel decreases with higher temperature? What happens at higher temperature?
More scattering from the lattice.
Yes, phonon scattering goes up. Therefore, 1 over mu phonon keeps decreasing. Well, mu phonon keeps decreasing. 1 over mu phonon keeps increasing. And therefore, this harmonic mean decreases even further, okay? But as long as I'm at, say, room temperature, all devices will have this universal dependency on mobility. And the mobility decreases as this transverse field goes up because, as I said, remember the sandpaper example? So that's your sandpaper. So I'm kind of pushing these electrons tighter and tighter against the sandpaper, making it harder and harder for them to flow from the source to the drain, okay? So what is this effective field that you have to use to get this universal curve? That's shown in this next plot, where once again, as I said, it's basically the vertical field measured in the middle of this inversion layer. Suppose I have an inversion layer of that thickness. It's this field defined at the middle of this inversion region, sort of an average field, okay? Which kind of makes sense, right? I mean, you have the highest electric field right at the surface, and then as you go deeper and deeper in the bulk, at some point there's no band bending. The electric field goes to 0 once you go up beyond the depletion region. So this is the plot of this transverse field Y, EY, as a function of depth Y, okay? So at the surface, you have the highest field, and then once you go past this depletion region, the field goes to 0, okay? But then in between, if we do the math, you'll see it varies linearly with 2 different slopes. The question, of course, is why? Well, you can get that by using this. You can solve the Poisson equation, okay? And in this case, we're solving the Poisson equation by approximating the inversion charge density as a rectangular distribution with a large height. And then the depletion charge density, also rectangular with a lower level, because that depends on Q, N, A, W, right? That's a doping concentration. While this depends on the inversion electron density, which can be much, much higher depending on the gate bias, okay? So then get the electric field. What you can do is you can draw this Gaussian pillbox shown by this dotted rectangle, and you can look at the field lines coming out of it, okay? That's Gauss's theorem, right? So that if I look at the field lines here, of course, are 0, right? The divergence of the displacement, D, okay, del dot D, which is del dot epsilon times electric field, sorry, epsilon times electric field, is equal to the charge enclosed, right? You can bring epsilon over here. So you can see that, the charge enclosed is the total depletion charge plus, in the middle, half of the inversion charge, right? So you define this average electric field as depletion charge plus half of the inversion charge. Okay. You can do the same kind of thing for PMOS, and you'd think that it should also be half of the whole charge, but because of details of the whole the valence band structure being more complicated, people find experimentally that instead of half, you take the average as 1/3. Those are details that if you take a grad class, you'll find out. Okay. So the key message, however, is if you plot the mobility as a function of this average field in the middle of this inversion region, all mobility data, regardless of what the parameters of the transistor are, lie on an universal curve. The only dependence is on temperature of the device because of this phonon scattering. Okay. I guess we have a few more minutes. All right. The other thing that I hinted at is the so-called subthreshold characteristics or subthreshold slope. Okay. That is, as I said, if you plot ID as a function of VG, you get this linear dependency going to 0 at VT, but in practice, current don't go to 0, right at VT, it'll slowly go to 0. And this conduction below threshold is called subthreshold conductance, which is what I'm showing over here as a function of VG, but now not on a linear scale as before, but on a log linear scale. So I'm plotting log of the drain current as a function of the gate voltage. And we'll find that if you do the math on a log linear scale or a semi-log scale, below threshold, that's my threshold voltage over here, the current doesn't go abruptly to 0, but it goes down exponentially to 0, right? How do I know it's exponential? Well, if I have an exponential dependency as shown over here, and I take log of ID, and I take the log of this exponential, I get a linear dependency on VG, right? So the current below threshold or the subthreshold current decreases exponentially with the gate voltage. And that slope is known as the subthreshold slope, okay? I call it subthreshold slope, but strictly speaking, you should call it inverse slope, okay? Because you see the units over here. So the units are, in this case, I get a value of 70 millivolts per decade. What does that mean? That means I have to change my gate voltage by 70 millivolts to change my drain current by 1 order of magnitude, 1 decade, okay? So it's really not the slope, it's actually reciprocal of the slope, okay? But the convention is to call it the subthreshold slope, okay? People are kind of sloppy. Now, the question is, do you want that number to be small or large? Well, in an ideal switch, you want to be able to turn it on and off abruptly, right? So you'd want that number to be as small as possible, hopefully 0 millivolts per decade, right? Unfortunately, you'll never get 0 millivolts per decade. The theoretical minimum that you get at room temperature is 60 millivolts per decade, and I'll explain why next class, okay? So we'll start off at this point. Any questions? All right, see you on Wednesday.